Okay, we are standing at a massive inflection point in technology right now. For the last few years, our AI models have been incredibly smart, right? But they've been largely trapped inside these little chat boxes. They answer our questions, sure, but they're completely unable to actually do anything about them in the real world. Well, that is changing, and it's changing rapidly. AI agents are suddenly gaining unprecedented abilities to take autonomous action across our digital lives and our enterprise systems. And while that unlocks literally incredible productivity, it's simultaneously introducing some massive, unprecedented new security risks. So, in this explainer, we are going completely under the hood of the technology that's making all of this possible.
Here is our roadmap for today. We're going to start with the USB-C for AI, look inside the MCP architecture, confront the shadow AI threat, break down protocol-level vulnerabilities, and finally, look at a blueprint for security. Let's get into it.
Section 1. The USB-C for AI. How we're breaking AI out of isolation.
You know, modern large language models are absolutely brilliant, but fundamentally, they are isolated. They're frozen in time and completely cut off from your real-time, real-world context. To solve this, Anthropic introduced something called the Model Context Protocol, or MCP, and I just love this quote from their documentation. Think of MCP like a USB-C port for AI applications. It's a really brilliant analogy. Think about it. Just like a USB-C cable gives you one single way to plug all your devices into your laptop, MCP provides a standard, open-source way to plug AI applications directly into external systems. We are talking about direct connections to your databases, your Google Calendar, your Slack channels, your APIs, the whole shebang. Instead of having to build custom integrations for every single AI model and every single app, MCP creates one universal language so they can finally talk to each other.
Now, it's absolutely crucial to distinguish MCP from something you're probably already familiar with, RAG, or Retrieval Augmented Generation. While RAG is basically a passive, one-way street where the AI simply reads data to answer a question, MCP is entirely dynamic. It facilitates a real two-way interaction. It doesn't just read your calendar, it can proactively book a meeting for you. It doesn't just read a database, it can write a brand new customer record into it. It really empowers these models to transition from being just passive advisors to actual autonomous actors taking real actions on your behalf.
Moving right along to Section 2, inside MCP architecture. Let's look at exactly how this protocol functions.
So, the engine powering this protocol relies on three distinct building blocks. First up, we have tools. These are actively controlled by the AI model itself. You can think of tools as executable functions, like searching for flights or sending an email, that the model actively decides to use based on whatever you asked it. Second, we have resources. These are controlled by the application and represent passive read-only data, like your calendar availability or past travel documents. They basically provide the context. And third, we have prompts. These are controlled by you, the user. Prompts are essentially these pre-built instruction templates that tell the model exactly how to combine those tools and resources to achieve a specific goal. Think of it like giving it a recipe.
Let's ground this abstract architecture in a real-world scenario, okay? Imagine a multi-step travel planner. Say you ask your AI to plan a trip. In step 1, the AI uses MCP to gather resource context. It hits up your calendar server to see when you're actually free, and it checks a travel database to look at your past preferences. Then, moving to step 2, armed with that context, the AI actively executes tools. It reaches out to an airline server to search flights, and maybe a weather server to check the forecast. Finally, in step 3, it synthesizes all of this and takes action. It uses tools to book the hotel and even draft an email to your travel companions. It's a complex, multi-step workflow happening seamlessly across a bunch of different external servers, all being coordinated by the AI using MCP.
Which brings us to Section 3, the shadow AI threat. We really need to talk about the governance gap here. All right, now we have to pivot to the dark side of this technology. I want you to seriously consider this for a second. What happens when an autonomous AI goes rogue? Remember, these agents are explicitly designed to be independent and goal-driven. They have this insatiable appetite for data, constantly querying APIs, writing code, and making decisions all across your company's systems. Without incredibly strict human-in-the-loop oversight, an agent trying to quickly satisfy a goal could easily push boundaries. It could access restricted data or initiate complex workflows that just leave a total trail of chaos in its wake.
And if you're sitting there thinking, well, this is a future problem, look at the staggering number from Okta's recent research. 91% of organizations are already actively using AI agents today. The deployment of this technology is moving at absolute light speed, far outpacing the security infrastructure that we actually need to protect it. And this brilliantly, or maybe terrifyingly, illustrates the reality of that rapid adoption. Of those organizations deploying these powerful agents, 44% have absolutely zero governance frameworks in place. Nothing. Almost half of the enterprise world literally cannot answer basic questions like, where are these agents in my ecosystem? What data can they even access? And who is actually accountable for them? This massive blind spot is creating an explosion of what security researchers are calling shadow AI. Basically, invisible, unaccountable, non-human identities operating right inside corporate networks.
Let's dive deeper into this in Section 4, Protocol-Level Vulnerabilities. We're looking at the architectural flaws. So, as if the enterprise oversight problem wasn't bad enough, some groundbreaking research has exposed severe security flaws built directly into the MCP specification itself. There are 3 fundamental architectural vulnerabilities that affect pretty much all compliant implementations. First, there's an absence of capability attestation. This basically means an MCP server can just claim it needs arbitrary permissions, and the client has no real way to cryptographically verify if that's even true. Second, and this is highly critical, there is unauthenticated sampling. This means a malicious external server can send a message totally disguised as legitimate user input, which opens the door for direct server-side prompt injection. And third, implicit trust propagation. Because MCP is specifically designed to make tools work together, the AI's context window conflates data from all connected servers. If just one server is compromised, those malicious instructions can easily spread to and hijack the actions of other connected servers. It spreads like wildfire.
The data quantifies exactly how dangerous those architectural choices actually are. In tests of over 800 attack scenarios, when an AI uses standard, non-MCP integrations, the baseline attack success rate sits at around 26%. But watch what happens when you route those exact same tools through the MCP architecture. The attack success rate basically doubles to nearly 53%. MCP's deliberate choice to prioritize seamless composability, making sure all these tools can easily talk to each other, drastically sacrifices isolation, which hugely amplifies the attack surface.
So how do we solve this? Section 5, the blueprint for security. Let's look at a dual-layered defense.
The crucial point here is how we fix this. Because AI agents totally disrupt traditional identity management, we need a really comprehensive framework, specifically the paradigm developed by identity experts like Okta. You cannot just bolt security on after the fact anymore. You have to operate on 2 layers simultaneously. First, you have to secure every agent by design. This happens at the developer level, embedding secure token vaulting, robust authentication, and fine-grained data authorization straight into the agent's code from day one. Second, you must secure all agents from a single control plane. This is the enterprise IT level, using an agent registry to track identities, enforcing lifecycle management, and having a kind of emergency universal logout switch to kill an agent's access across all systems the very second you detect anomalous behavior.
But to solve those specific vulnerabilities baked into the protocol itself that we talked about earlier, researchers have actually proposed a backward-compatible extension called ATTS-MCP. It patches those architectural flaws by enforcing 3 new rules. Number 1, capability attestation. Servers must now mathematically prove they have the right to their permissions using cryptographically signed certificates. Number 2, message authentication. Every single piece of data sent back and forth must be signed, proving its integrity. And number 3, origin tagging. The protocol must mathematically distinguish between a prompt that came from a real human user and a prompt that came from an external server. This basically totally shuts down that deceptive prompt injection vector.
And the best part? The data proves that this protocol-level solution actually works. By implementing ATS-MC, security researchers were able to drastically slash that amplified attack success rate. They brought it all the way down from that terrifying 52.8% to just 12.4%. And they did all of this while adding only a negligible few milliseconds of latency to the system. It's a real game changer.
So let's wrap this up. The Model Context Protocol is truly unlocking the potential of AI, turning them from passive chatbots into incredibly capable digital employees. But this major shift demands a total rethink of our digital security. As AI shifts from simply answering our questions to taking autonomous actions across our networks, I want to leave you with this. Is your infrastructure genuinely ready to verify the identity and limit the blast radius of the agents acting on your behalf? Thanks so much for joining me on this explainer, and remember to keep questioning the technology that's shaping our world.